Hi, welcome to MooMooMath. Today we are going to look at probability, the counting principle, permutations, and combinations. Some general probability. So on the first slide, I have some warm-up questions, and they're just prerequisite skills that you need for probability. So I want you to evaluate 10 factorial, 4 factorial times 3 factorial, and then 6 factorial divided by 4 factorial. If you don't know what a factorial is, I've got an example up here. 5 factorial is 5 times 4 times 3 times 2 times 1, so it multiplies out to 120. So 10 factorial, you want to maybe grab your calculator and multiply it out. So you have 10 times 9 times 8 times 7 times, let's go back, times 6 times 5 times 4 times 3 times 2, and of course times 1 won't change it, but we'll put it up there. Okay, so what is that? 3,628,800. So our answer is 3,000,000, whoops, let me change my pen back right here. 3,628,800. Okay, so let's take 4 factorial times 3 factorial. And 4 factorial times 3 factorial would be 4 times 3 times 2, and of course times 1 won't change it. Then times 3 times 2 times 1, and that gives us 144. So just hope you're kind of following along how to do this. And then 6 factorial divided by 4 factorial. Instead of putting this in the calculator, I'm going to write this one out. Okay, 6 factorial is 6 times 5 times 4, and then 4 is going to be times 3 times 2 times 1. So really that's just 4 factorial. So I have 6 times 5 times 4 factorial, all divided by 4 factorial, which would be 4 times 3 times 2 times 1. So guess what? Those cancel. So the answer is just simply 30. So a real quick way to do it when you're dividing. You can actually just cancel part of that factorial out. Okay. So now I wanted to show you how to use your calculator to evaluate this 12C3 and 7P3. These are combinations and permutations, which I'm going to teach you in a few minutes, but I wanted to go ahead and show you how to put those in the calculator so we could just jump straight in. So what you're going to do to evaluate these, you're saying 12 with a combination of 3. So you're going to type in your calculator 12. Then you're going to go to the math button and you're going to go over to probability. So math, and then scroll over, and you can see the third choice is a combination. So you're going to choose that by hitting enter. And whoops, something happened there. Let me clear that out and try it again. So 12 math, scroll over to probability, whoops, and I'm going to choose 3. I think I went too far on that. And then choose 3. Okay, so that is going to be 220. Now that involves combinations and permutations, and I'll show you the equation for that when we get to that. And then the second one is a permutation. It's kind of the same concept. You're going to take 7 with a permutation. So take your math button. After you type in 7, scroll over to probability. And this time go to the second choice, a permutation, and we're going to choose 3 and hit enter. And so that is 221, or 210. And that's how you use your calculator. So those were just some prerequisite skills we needed for this lesson. We needed to know factorials. We needed to know how to type in a combination and a permutation into our calculator. Okay, so let's start with the first concept, which is the fundamental counting principle. Okay, in this case, we're going to have 2 events. We're going to name those E sub 1 and E sub 2, event 1 and event 2. The first event, it can occur in m different ways. So we're going to use m sub 1 to refer to the ways that we can count the first event. And then a second event, or e sub 2, occurs in m sub 2 different ways. And then what we're going to do to find the number of ways the two events can occur, we would multiply those two different ways together. So the result would be m1 times m2. Okay, so let's look at a scenario so you can see it as an actual problem. It says you go to Applebee's for their $10 special. There are 4 appetizer choices, 8 drink choices, 5 main dish choices, and 2 dessert choices. How many different ways can you order your meal? Well, first of all, we need to figure out how many events are occurring. Well, in this problem, we have an appetizer, a drink, a main dish, and a dessert. So we actually have 4 events. So what I like to do is just go ahead and draw myself 4 blanks, one for each, representing each event. Okay, then I'm going to write down my possibilities, how many ways each event can occur in each of the blanks. So I've got appetizers first, so I've got 4 appetizers, and then I have 8 drink choices, so 8 drink choices, and then 5 main dishes, and then I have 2 desserts. Now for the counting principle, all I do is multiply all these together. So let's grab my handy dandy calculator, and I'm going to multiply together 4 times 8 times 5 times 2. And I get, let me pull this back out, 320 different ways I can go to Applebee's and get a meal 320 different ways. So I could go almost every day the whole year and get an order from the menu and get a different combination or different meal each of those times. So it's kind of interesting to see how many different ways you can do it. So let's look at a couple other counting principles. Okay, we've got a Social Security number. I think most of you have a Social Security number, and there are 9 digits in that number. How many Social Security numbers are possible? Well, you have to think, well, how many events do I have going on? I have 9 events, one for each digit. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Trying to draw straight, didn't draw straight, but that's all right. Okay, then you are going to multiply all these events together. So I'm going to multiply these, and I've got to start thinking how many different possibilities, how many different ways can I pick the first digit? Well, I have the numbers 1 through 9, plus we can't forget about a 0. A 0 counts also. So you actually have 10 different numbers to choose from, including 0. So the first digit could be 0. It doesn't say it can't be. So I have 10 choices. Well, how many choices do I have for my second digit? I have 10 more choices because I can repeat numbers. So I'm going to have 10 choices for all 9 positions. So it's just going to be 10 times 10 times 10, 9 times. Okay, we can also write this as 10, to the 9th power, 10 to the 9th. So let's grab our calculator and pull that back out, and we'll actually figure out how many Social Security numbers can be created. It's going to be a lot. Wow. So I've got 1 with 1, 2, 3, 4, 9 zeros after it. Okay. So let's write that in that. Sorry about that. Let's grab my pen here. Whoops. Grab my pen, and I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So what's that? A billion different numbers. We have 1 billion different ways to get a Social Security number. So that's a lot. Okay, let's try the phone number problem. Okay, we have a 7-digit phone number. How many are possible if the first digit cannot be a 0 or a 1? We know if it's a 0, then it's going to call the operator. And if it's a 1, it's going to call long distance. So we have to eliminate those choices. So how many events do we have going on? Well, we have 3 in the front, and then we usually have a dash here, and then 4 in the back. So we have 7 different positions or 7 events. How many possible outcomes, or how many ways can I pick the first digit if I can't use a 0 or a 1? Well, that means I normally have 10, but I'm taking 2 away, so I only have 8 choices. But then for the second position, I have 10. I can put a 0 and a 1 there, and I can put a 10 here. I can put a 10 here. I can put a 10 here. I can put a 10 here and here, because all of these have 10 different choices. So I have 10, what, to the 6th power, all times 8. So what's 10 to the 6 times 8? Let's take 8 times 10 to the 6th power, and boom, I have, what's that, 1, 2, 3, 8 million different ways. Yep, 8 million, that makes sense. I would have 8 million different phone numbers. Now, as you know, there are probably more than 8 million phone numbers in the world. So we have to add area codes that are 3 digits, and that adds a whole bunch more possibilities. So you could figure that out too if you wanted to. Okay, let's see how this problem's slightly different, but we can still use the counting principle. Okay, how many different ways can 5 cars be arranged on a car carrier truck with room for 5 vehicles? So let's just think about what we have. We have one of these trucks that has a top floor and a bottom floor, and then it's got an engine up here. I like to draw a little picture of it. Okay, and here's the front light, and here's where the driver is. Okay, and it needs to load cars up here. Well, we have a spot for 1, 2, 3, 4, 5 cars, something like that. There may be 3 on top and 2 on the bottom. But anyway, we have a spot for 5 cars. How many different ways could we arrange these 5 cars? Well, what's different about this is once we place a car, we can't use it again because we've already placed it. So we have to think about our 5 events. We have 5 events going on because we have 5 positions for 5 cars. So let's draw our 5 lines to represent each event. Okay, now for spot 1, how many different cars can we put up? If we have these 5 cars lined up, well, we could pick any of them. So we would have 5 choices. But then for the second position, once we've put a car, let's just say we put the little blue car up there, we now have 4 choices. And then once we put a car up, let's say we put the red one next, we would then have 3 choices, and then 2, and then 1. So really what we've done is we've created a factorial. Well, what's 5 factorial? Well, I'm not going to grab my calculator because this one's pretty easy. That's going to be 20. And 20 times 3 is 60. And 60 times 2 is 120. So I have 120 different ways to arrange the cars. That's how many different ways I've got. So there you go. We got 120 different ways to put them on the truck. Okay, so that's kind of the end of the counting principle. Now let's look at permutations. Okay, a permutation is a similar situation. It's the number of different ways of ordering elements such that one element is first and one is second and one is third and so on. So it's similar to placing the cars up there as we did in the counting principle, but each one has a specific position. So really you could look at the car placement almost as a permutation. Now in the past, I like to relate this permutation to a locker combination, okay? A locker combination is actually not a locker combination. It's a locker permutation. And why? Because the order that you turn the dial on the locker, on the lock, the order matters. So if you have, let's just say your locker combination is 4, 30, and 25. You have to put it in that order or your locker's not going to open. You can't make it 25, 30, and 4 or 34 and then 25. It has to be in that order. So a permutation is actually the counting principle, but order matters. Okay, so let's look at this one. How many ways can you arrange 6 letters in 6 positions? So in this case, I've got 6 letters, A, B, C, D, E, F, but that means I have 6 events going on, so I'm giving myself 6 spots. Okay, I'm going to multiply each one of these spots together, but I got to think, well, how many different ways can I choose my first letter? Well, 6. I have 6 choices. But once one's placed, I have 5, then I have 4, then I have 3, then I have 2, then I have 1. So really, guess what? That card problem was a permutation. But it's a type, it's a special type of the counting principle. Okay, so let's multiply all this together. This is going to give me 30 and 34. 30 times 4 is 120, and 120 times 3 is 360, and 360 times 2 is 720 different ways that we could arrange the 6 letters into different patterns. Okay, now let's look at this one. What if there were the same 6 letters, but we only choose 3 of the positions? What if instead of having 6 events, we only have 3 events? Well, that's going to change things. Okay, so we have, for the first choice, we still have 6. For the second choice, we have 5. For the third choice or position, we have 4 choices. So really, we only end up with 30 times 4, which is 120 different ways to choose those letters. Well, we can use the permutation equation to figure that out, where n is the total number of possible choices. In this case, it would be 6. R represents how many we're choosing, how many positions we have. In this case, this one's 3. And then we plug this into a factorial equation where we have n factorial, where n is 6. So let's write 6 factorial over 6 minus 3, which is n minus r, all factorial. So we're going to take the difference between the two and take that factorial. So in this case, we have 6 factorial over 3 factorial. Well, earlier, remember how I showed you how to do factorials? So that 6 factorial, 6 times 5 times 4 times 3 to 1, which is just 3 factorial, all over 3 factorial, where the 3 factorials cancel out. And yes, indeed, we got 6 times 5 times 4, which ends up being that 120. So you can kind of think of it 2 different ways. You can use the equation, or you can just think about the positions and the possible outcomes. Okay, so here's one. We have to think about positions. There are 8 horses in a race. How many ways can they finish as first, second, and third place winners? Okay, that's order's important. Why is order important? Because you're talking about first, second, and third place. So you could have the same 3 horses finish in a different order, and it makes a new solution or a new answer, a new outcome. So you have to think about that. That's what a permutation is. So let's do it both ways. We'll first do it with the counting principle, thinking about the events. So we have 3 events occurring because we have 3 outcomes. We have a first place winner, we have a second place winner, and we have a third place winner. So we have to think about how many choices we have. Okay, those are the events. How many ways can we have a winner with 8 horses? Well, 8 choices. how many ways. Once 1 has won, we have 7 choices for the second place and then 6 choices for the third place. So let's get our calculator out and let's multiply 8 times 7 times 6. And that gives us 336 possible ways those horses can finish first, second, and third. Okay, now let's look at it with the formula. Now, here's our formula. I'm going to go back and pull this formula. Okay, I'm going to erase this real fast so we can look at it a little bit better. Okay, we're going to have n factorial over n minus r factorial. So just wanted to show you that. So n in this case is how many total do we have? Well, we have 8. And we're going to take a permutation because order matters. And we want 3 positions. So it's 8 permutation 3, 8 choosing 3. And that means we're going to have an 8 factorial, which is n factorial, over n minus r. So 8 minus 3 factorial. And that gives us 8 factorial. I'm just going to go ahead and subtract the bottom so you can see it. And that's 5 factorial. So really, we're just taking 8 times 7 times 6 times 5 factorial all over 5 factorial, which cancels. And I have 8 times 7 times 6, which is 336. So when we talk about showing our work, this is actually what we mean. Writing the formula, showing that we understand what factorials are, and that's how we show our work. Okay, now let's talk about a special case of a permutation. Suppose you have a set of n objects, and some of them repeat. So you have n sub 1, one of the objects is one of a kind, n sub 2, there's 2 of a kind, n sub 3, there's 3 of a kind, and so on. So you have repeating objects in a group. Okay, to find the number of permutations, we're going to take n factorial, which is the total number, divided by n sub 1 factorial, n sub 2 factorial, or whatever's being repeated. So let's look at the case of the banana. Okay, here's the case of the banana for our distinguishable permutations. And how many distinguishable ways can the letters banana be written? Well, remember, we have in banana 1, 2, 3, 4, 5, 6 letters. So for our permutation, wouldn't we take 6 factorial? And then we would choose 6 ways. But because A occurs 3 times, those positions are not going to be unique, because whether that A is the first A or the second A or the third A, we don't know. Those are repeating in our pattern. So I have to divide by 3 factorial to represent the letter A. Then N, it occurs twice. So I have to divide by a 2 factorial because it occurred twice. Now, the B I don't really have to worry about because it's 1 letter and it would be 1 factorial. So that's just 1. So I've got to take 6 factorial divided by 3 factorial and divide times 2 factorial. So I'm going to write the entire sequence down. So I've got 6 times 5 times 4 times 3 times 2 times 1. And I'm going to divide that by 3 factorial, which is just 3 times 2 times 1. And I'm going to write it under there because I know those can cancel. Then I have a 2 factorial. Well, 2 factorial is 2 times 1. So I'm going to write that one all out. Now let's cancel out what we can. We can cancel the 3s, we can cancel the 2s, we can cancel the 1s. And then 2 does go into 4, so I could reduce this by 2. And then really, I'm just multiplying together 5 times 6 times 2. So that's 60 different ways the letters in the word banana can be arranged to make unique patterns of 6 letters. And that's how you figure out a distinguishable pattern. So that one's a little bit different because we have to think about repeating choices in a pattern. Okay, so now we're on to the next topic. This one is combinations. So in probability, you have permutations and you have combinations as well as the counting principle. So we're looking at our third option, which is combinations. A combination is when counting the number of possible permutations in a set where order is important, but in a combination, the order is not important. So when you're doing a permutation, order is important. When you're doing a combination, let me highlight this. When you're doing a combination, order is not important. You treat it similarly, but you have to read carefully and decide if the order is important. So let's start with this first scenario. Given a group of 10 students, 3 of them are chosen to pick up books for the class. Okay, so we're choosing a group of 3 students to go pick up books. That group of 3 is the same group of 3 whether I pick Sally first and Eddie and John, or if I pick John first and then Sally and Eddie. It doesn't matter. It's one group of students. So anytime you have a group where the order doesn't matter, that one's a combination. Okay, so how do we figure it out? Well, we're going to use this little formula for combination. We're going to take N choose R, or NCR, where N is the total number of participants. In this case, it's 10 students. And then R is how many we're choosing, which in this case is 3. So this is going to be 10 with a combination choosing 3. So in our formula, we're going to put 10 factorial on top. And then on the bottom, we're going to take 10 minus 3 factorial, all times another 3 factorial. So we're dividing twice on a combination because we're going to have less possible outcomes than a permutation. A combination is always going to have less than a permutation with the same group and the same choices, because you're dividing twice and the groups don't, the order doesn't matter, and that's why. So take a minute and kind of think through that. So let's write this out. So I have a 10 factorial over, this ends up being a 7 factorial because 10 minus 3 is 7. So let's write it out as 10 times 9 times 8 times 7 factorial on top, all divided by 7 factorial times, and I'm going to write the 3 out, the 3 times 2 times 1, so we can do some reducing. Okay, the 7 factorials cancel, and then I can reduce 3 and 9 just to 3, and 2 and 8, I can reduce that to 4. So really, I'm just taking 12 times 10, so that's 120. So that means there are 120 different ways I can choose 3 students to go get books from a group of 10 students. That's how a combination works. So let's look at another combination. An IRS agent must audit 12 of the tax returns from a collection of 22 flagged returns. How many different combinations are possible? So let's say he's going to get all 12 done today. Well, it doesn't matter if he starts at the top of the pile or the bottom pile to pick the 12. He's just got to pick 12. So what's that going to look like? Well, I've got 22 files to choose from, the total number, and I'm choosing from there as a combination 12. So I'm going to have 22 factorial over 22 minus 12. So my difference is 10 factorial times 12 factorial. Well, you know what? That's a little bigger than I want to handle. So I'm going to grab my calculator, and this time I'm going to use my buttons. Whoops, buttons to calculate that. So I'm going to type in 22, and I'm going to go to the math button. I'm going to go over to probability. I'm going to choose, in this case, a combination, and I'm choosing 12. And that means there's 646,646 different ways I can choose to check tax returns today. And what unit would you put? I would just put ways to choose files. There you go. And that's how you figure it out. Now, it's a little tricky. What we're going to do now in permutations and combinations is try to figure out which is which. Which one is a permutation and which one is a combination. So we have to read each problem very carefully. So let's look at number 1. Remember, permutation, order matters. Combinations, order doesn't matter. So, number 1, a union must select a president, a vice president, a secretary, and a treasurer from 16 available candidates. How many different slates of officers are possible if one candidate is nominated for each office? Okay, so you have to think, does the order matter? Does the position matter? And in this case, could I choose 4 students to be president, vice president, secretary, and treasurer, and take the 4 students, reorder them, and come up with a new possible slate? And the answer is yes. So this one has to be a permutation. So how would I put it in my calculator? I would do 16 with a permutation of 4 positions. So let's grab our calculator and do 16 math, probability, permutation this time, and I'm choosing 4 positions, and that's 43,680. So this one has 43,680 different ways to choose for the election. Okay, so let's try the next one. A union must select 4 board members from 16 available candidates. How many different slates are possible? Now this one's different because we just have board members. They're not assigned to a position. So that one is a combination. So I'm going to do 16, choose 4, but this time it's a combination. So let's do 16, math, probability, choose a combination, and choose 4. Now, the combination will have less possibilities. It's only got 1,820. And why is that? Because the order didn't matter. The same group of 4 aren't going to be assigned to a position. So that's how come we can do it. Okay, so let's look at a summary kind of what we did. Okay, first we looked at the counting principle. And that's just when you look at different ways to choose from like a menu or maybe an outfit from a group of clothes, different ways you can multiply your possibilities together. Then we looked at permutations. That's another way to count outcomes. Okay, for a permutation, the order matters. So remember, you have a locker permutation, not a locker combination. And then combinations. A combination is when the order of choosing your options, when the order doesn't matter, when you're choosing in a group. So whenever you have some choices, the solution group or what you're choosing ends up just being a group where the position does not matter. And that's kind of the summary of this lesson. I hope this lesson on the counting principle, permutation, and combinations was helpful.